Okay, so today we're going to talk more about probability. Now, we're going to start talking about laws of probabilities, and we're going to kind of continue that through the rest of this chapter. So the first probability law you should already know, which we learned from last class, is that the probability of 0, if the probability of something happening is 0, that means that it's impossible. It can't happen. It's not going to happen. And then probability law number 2 says the probability of something is 1. That means it has to happen. It's certain. It will happen. Probability law number 3, you also know, it's that the probability of something happening has to be between 0 and 1 inclusively. So this is all just like what we learned last class period with that probability line, that 0, 1/2, and 1. If it's 0, it cannot happen. It's impossible. If it's 1, it's certain. It will happen. If it's 1/2, that means it's 50-50. If you get a probability of something happening as 0.5, it's 50-50. If it's between 0 and 1/2, what did we say it was? Unlikely. And between 1/2 and 1, what was it? Likely. Very good. So that probability line is really helpful for like when you get a number back, what it means. Now, probability law number 4 says, and this is kind of hard to read, but that's what we're learning. We're learning how to read math. The probability of the first event plus the probability of the second event plus the probability of the third event, all around how many that you have, the outcomes must equal 1. So the sum of all probabilities has to equal 1. Okay? You cannot have probabilities be more than 1. It will not work. So that being said, let's talk about a compound event. A compound event is an event that is defined by combining 2 or more events. Can be more than 2. So suppose that the admissions department of Fort Hays believes that anyone who obtains a GPA of greater than 2.0 or achieved a score of at least 20 on the ACT would be a good prospect for a future student. So it says, let the event A equal you have a GPA greater than 2.0, right? So here's a visual we've got going on. If we're talking about event A, that means you have a GPA that is greater than 2.0. Okay? And then event B means that you get at least a 20 on the ACT. Okay? The union is the set of outcomes that are included in event A, event B, or both. Okay? Now here's what's important about that. The union is a set of outcomes that are included in event A, event B, or both. Now the union means we're going to put them together. So that would be event A, only event A, right? Only event B, or both. Everything in the middle. We okay with that? So this is going to be the union. Now, do you guys remember the symbol for union? What does it look like? U, right? Like a big old capital U. So the union would look like A union B. Okay? Now, do you guys remember what the phrase was that you learned? We learned it back in Algebra 1. You probably refreshed it in college algebra and Algebra 2. This union is what? Greater than yours, right? Disunion greater than yours. That means a disjunction was a union. And what kind of statement was it? An or statement. So an or statement means you're going to have a union. So again, Fort Hays believes that anyone who obtains a GPA of greater than 2.0 or achieved a score of at least 20 on the ACT would be a good prospect. That means it is a union. An or statement means it's a union, which means that an and statement would be what? What would an and statement be? An intersection. An intersection. So we have two different compound events. We have or and we have and. Or means union, and means intersection. Now the intersection is the set of all outcomes that are included in both event A and event B. So again, here's my Venn diagram. Where would the intersection be located? Just in the middle. This is my intersection right there. So A intersection with B. A intersect B is that part in the middle. Okay? The next thing we're going to talk about might be a new concept to you. The next thing we're going to talk about is the complement. The complement of an event A is the set of all outcomes in the sample space that are not in A. So here's a really good visual representation. I have kind of a Venn diagram going on. So this event is event A, okay? Everything that is not happening in event A, which everything out here, is the complement of A, okay? So everything that is not included in event A is the complement of A. Now, you will see the complement written in a couple of different ways. So the first way, which you can see here, is A, and it has like a C as an exponent. That is the complement of A. Another way you might see the complement is like A, and then it has like a tick mark, A prime. That's another way you'll see complement. And then another one is like a bar above it. Those are the three ways that they might tell you that you're looking for a complement. Okay? Those are the complement. Now, an example to help you understand this, if the event A is the annual income is greater than $50,000. So my annual income is greater than $50,000. Okay? That is the event. The complement of that is everything not greater than $50,000. So everything not greater than $50,000 would be income that is less than or equal to $50,000. Now, it's important that you understand that since the event was just greater than $50,000, the complement is less than or equal to. All right, so be careful with that. So, probability law number 5 comes from the complement, and it says the probability of the complement of an event happening is actually just 1 minus the probability of that event. So if the probability of you having an income greater than $50,000 is 0.4, then the complement of that, since we know that compound events cannot have a probability greater than 1, is 1 minus that, which would be 0.6. Okay? So to find the complement, you just take 1 minus the probability. Now, math operations and their complements. So if you see an operator like an equal sign, they say the probability of something being equal to something, its complement would be not equal to. Okay? If you have greater than, its complement would be less than or equal to. If you have less than, its complement would be greater than or equal to. If you have none, if it says the probability of none, then its complement would be at least 1. Now also, if you had less than or equal to, its complement would be greater than. If you had greater than or equal to, its complement would be less than. Okay? Those are just some things that you can, or you will see. Now, a good example of none and at least 1, because that one's really hard to wrap our head around. Let's say none of the scouts are selling cookies, right? That's what I'm saying. None of the scouts are selling cookies. Well, the complement of that happening is just something to disprove that. So the complement, so if this is A, my complement would be 1 scout is selling cookies. Because if I say, man, there are no scouts selling cookies, and then someone knocks on my door and they're like, hi, would you like to buy some cookies? That is the complement. Now, the next thing we're going to talk about is the difference between odds and probability. Odds and probability are not the same thing. You guys will hear this all the time. Something will happen and some old geezer on the sidewalk will be like, well, what are the odds of that happening? That is not the same thing as probability, okay? Odds in favor of an event occurring, check this out, is the probability of something occurring over the probability of not that happening. Wow, I can't believe I just said it like that. The probability of something happening over the probability of it not happening. In layman's terms, or what we just figured out, it's the probability of something happening over the probability of its complement. Okay? Now, the odds against an event occurring is the opposite. It's the reciprocal. It's the probability of a complement happening over the probability of it happening. So, on number 1, it says the odds of a horse winning a race are 3 to 1. So again, you can see it written like that. Sometimes you'll see it written like that. Sometimes you'll see it written like that. It says, what is the probability that the horse will win the race? Okay? The odds of a horse winning are 3 to 1. What is the probability that the horse will win the race? So currently, it tells me that the odds are 3 winning to 1 losing. Are we okay with that? 3 winning to 1 losing. That's what the odds are, the probability of it happening over the probability of its complement. So there are 3 winning, 1 losing. How many total outcomes are there in this? There are 4 total outcomes. So the probability of winning is what we want to have happen over the total outcomes. So what we want to have happen is winning. And how many winning did they say there were? 3. Over the total, which we said is what? 4. And that's going to give me 0.75, which is what as a percentage? So he has a 75% chance of winning that race. So odds of 3 to 1 is 75%. Are we okay with that? In the game of roulette, the roulette wheel contains the numbers 1 through 36, alternating between red and black. There are 2 green spaces numbered 0 and 00. Okay? So my question to you before we even start here, how many slots are on a roulette wheel? 38, because we have numbers 1 through 36 and 0 and 000. So I'm just going to come over here and write that note. There are a total of 38 slots on a roulette wheel. Okay? Part A says calculate the probability of the roulette ball landing on a red pocket. So we said 1 through 36 alternating between red and black and 2 green spaces. So how many red spaces are we going to have? 18, because we took that 36 divided by 2, and that gives me 18 red spaces. So the probability of landing on red is going to be the 18 red spaces over how many total were there again? 38. So you can either simplify that fraction, which would be 9 over 19, or put it as a decimal, which would be what? 0.47. So what do we think? Do you think it's going to have or land on red? I mean, technically, according to our probability line, what would it be? It would be unlikely, but it's pretty close to what? 50-50. Okay? So, on part B, calculate the probability of the roulette ball not landing on a red pocket. Now, there are a couple of different ways you can do this. The first way is to think about this as, like, what does that mean? If it's not going to land on a red space or red pocket, what does that mean it would land on? Black or green. Well, how many blacks do we have? 18. And how many greens do we have? 2. So the probability of it not landing on a red pocket would be 20 over 38, right? Or, check this out, this is where the complements really come in handy, okay? The probability of it not landing on a red pocket is just the complement of the probability that it will. So I can come here and I can say the probability of the complement of red is just going to be 1 minus the probability of red, which is 0.47, which is going to give me 0.53. So tell me the probability of it not landing on a red pocket is going to be what? Likely. Okay, but again, it's pretty close to 50-50. Now part C is a little bit different. Part C says calculate the odds in favor of the roulette ball landing on red. So odds in favor is the probability of that event divided by the probability of the complement of that event. So the probability of that event is going to be 9 over 19. And I'm going to divide that by the probability of the complement of that event. Now the complement of that event I got as a decimal, but check this out, guys. If the probability of that event is 9 over 19, what's the complement of that? 10 over 19, whatever's left, right? So divided by 10 over 19. Now you can use your calculators. Even if you use decimals on this, I really wouldn't have cared. I'm just trying to get you to understand what we're doing. But you know as well as I do that we probably shouldn't divide fractions. Instead, we should multiply by the reciprocal. So 9 over 19 times 19 over 10, which is going to give me 9 over 10. So the odds in favor of the roulette ball landing on red are 9 out of 10. Those are the odds. After taking this class, you will be scared to go to Vegas, as you should be. All right. Yes. This guy? The probability of the event happening right here. Yeah? Any other questions before we move on? Lainey? She fine? Jocelyn, is she lying? She's lying. Okay. Now, the next thing we're going to talk about are mutually exclusive events. Two events are mutually exclusive if they have no outcomes in common. For example, drawing a jack from a deck of cards and drawing a 7 from a deck of cards. They are mutually exclusive because they have no outcomes in common, right? You cannot draw a jack that is also a 7. Are we okay with that? They are mutually exclusive. Now, probability law number 6 says that if the events A and B are mutually exclusive, then the probability of their union, so A union B, equals the probability of A plus the probability of B. So let's figure that out. What is the probability of drawing a jack out of a deck of cards? 4 out of 52, which is what? 1 out of 13, okay? And what's the probability of drawing a 7 out of a deck of cards? Again, 4 out of 52, which is 1 out of 13. So the probability of drawing a jack or drawing a 7, since they are mutually exclusive, just means we're going to take 1 out of 13 plus 1 out of 13. And what do we get? 2 out of 13, okay? Since they are mutually exclusive, to find their unions, we can just add them together, okay? Now again, if the events A and B are mutually exclusive, then their intersection is 0. So the probability of A intersection B has to be 0. Here's what that means. The probability of drawing a jack and drawing a 7 in the same draw cannot happen because they're mutually exclusive. They cannot happen at the same time, okay? So suppose that the probability of event A is 0.27 and the probability of event B is 0.19. If A and B are mutually exclusive, what is the probability of A union B? According to probability law 6, since they are mutually exclusive, I just have to add them together. So the probability of A union B is going to be 0.27 plus 0.19, which is 0.46. Okay? Mutually exclusive events are really simple. Just add them together. Now that leads me to probability law number 8. Probability law number 8 says that for any two events, A and B, the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. Okay? So here's the thing. Looking at my visual here, are A and B mutually exclusive? No, they are not. Okay? So you cannot just add them together because what do they have right here? They have some overlap, and that overlap is really important. So let's do an example, and I'm going to show you why it's important. Number 4 says, when drawing one card out of a deck of 52 playing cards, what is the probability of getting a heart or a face card? Okay, what is the probability of getting a heart or a face card? So event A would be drawing a heart, okay, and event B would be drawing a face card. Okay? So what would be in here? What would be in this overlap right here? A face card, that's a heart. How many face cards are also hearts? 3. We would have the Jack of Hearts, the Queen of Hearts, and the King of Hearts, right? Yes. Sometimes they will, sometimes they won't. The only time you have to be worried about it is if they're like, you have a deck of 10 cards. 3 are red, 2 are yellow, whatever, 5 are blue. Does that make sense? So the reason that sometimes they specify 52 playing cards and sometimes they don't, it's usually assumed. It's usually assumed unless they specify otherwise. Good question. Okay, so the probability of the union of these two events, so the probability of getting a heart or a face card would be the probability of drawing a heart plus the probability of drawing a face card, but you have to be really careful. They want you to subtract this intersection, and let's talk about why. Can you list me what are all of the hearts that I could draw? 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6, 7, 8, 9, 10, Jack, King, Queen, right? Ace, very good. Okay, those are all of the cards that you could draw that are a heart, right? Now, what are all of the face cards that you could draw? Jack of clubs, Queen of clubs, King of clubs, Jack of hearts, Queen of hearts, King of hearts, Jack of diamonds, Queen of diamonds, King of diamonds. What's the last one? Okay, so Jack of spades, Queen of spades, King of spades, right? Now, if you'll notice, this guy right here, the Jack, King, and Queen of hearts, and the Jack, King, and Queen of hearts were counted how many times? They were counted twice. They were counted once in event A, and they were counted once in event B. We don't want to count them twice. We only want to count them once, which is why, if you'll notice, they're only subtracting the probability of the intersection one time, and that leaves 1 available. Are we okay with that? So let's figure out what this is going to be. It says the probability of A union B is going to be the probability of A plus the probability of B, wow, minus their intersection, the probability of A intersection B, okay? Now, event A, we said, was drawing hearts, so the probability of hearts. Event B, we said, was a face card, so the probability of drawing a face card, minus their intersection, so the probability of hearts intersect face cards. Now, what is the probability of drawing a heart? How many did we say there were? 14? 13. So the probability of drawing a heart is 13 out of 52. Okay? What's the probability of drawing a face card? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? 12 out of 52. But then again, we know, we just saw that we counted the Jack, King, and Queen of Hearts 2 times. We counted them once here and once here. So we just need to take one of those times away. So what is their intersection? 3. There's only 3 of them that intersect. So we are going to subtract 3 out of 52. Now, from this point, you can use your calculator, whatever. We have common denominators here. So 13 plus 12 is 25, minus 3 is 22 out of 52. So the probability of A union B is 22 over 52, which is 11 over 26, which is approximately what? 0.42. So the probability of drawing a heart or a face card is impossible, unlikely, 50-50, likely, or certain. Unlikely, but it's pretty close to what? Pretty close to 50-50. All right, number 5. A card is chosen at random from a standard deck of 52 playing cards. Again, they just clarified just so you wouldn't have any questions. What is the probability that the card drawn is a king or a queen? Now, the first thing you need to do when approached with a problem like this, you need to determine if these events are mutually exclusive. Can one happen at the same time as the other? So can I draw a card that is both a king and a queen? No. So are these mutually exclusive events? Yes. So I'm a visual person. Here's what I do when that happens. I say, okay, here's my 2 events. One is drawing a king. One is drawing a queen. They are mutually exclusive. I cannot draw a card that is a king and a queen. Okay, there is no intersection. So that means to find the probability of the card being drawn being a king or a queen is going to be a mutually exclusive union. These ones are super easy. So that means the probability of drawing a king or a queen, and remember, or means union, is the probability of a king union queen. And since they are mutually exclusive, that just means the probability of drawing a king plus the probability of drawing a queen. Okay? What is the probability of drawing a king? 4 out of 52. What is the probability of drawing a queen? 4 out of 52. Now, some of you might be like, well, you're not simplifying. You can simplify if you want to. I'm just focused on the end answer, right? What is 4 out of 52 plus 4 out of 52? 8 out of 52. Now, on Hawk's Learning, they're going to give you two possibilities for your answer. You can write your answer as either a simplified fraction, so you cannot put in 8 out of 52. You would have to put in 2 out of 13. Or they say you can put it in as a decimal, and they'll tell you how to round it. Okay? This would be 0.15. They might have you round it to 4 decimal places. Okay? So on this practice, I'm writing out a lot. I'm showing you like what we're finding, what that means. That's so you have something to refer back to if you're like, I don't remember how to do this. How did she find this answer? When it comes to writing your answer, if you want the fraction, it has to be simplified. If you want the decimal, you have to round it correctly. Okay? Let's look at number 6. A card chosen at random from a standard deck of 52 playing cards. What is the probability that the card drawn is a king or a diamond? Since it says or, is this union or intersection? Union. So I want the union of a king or a diamond. So what do you guys think? Is this 2 mutually exclusive events? No, because can I draw a card that is a king and a diamond? Heck yeah, the king of diamonds. So my event is going to look like this. I'm going to have this event, which is kings, and this event, which is diamonds. And how many cards is in the intersection? Just one. What is it? The king of diamonds. So, to find the probability of the king or a diamond, so the king union diamond, that would be the probability of a king plus the probability of a diamond, but that king of diamonds is going to be counted twice. So we have to subtract the probability of a king intersection with a diamond. So what is the probability of a king? 4 out of 52. What's the probability of a diamond? 13 out of 52. And what was their intersection? How many did we say they intersected? 1 out of 52. What do we get? 16 out of 52. But again, because 4 plus 13 is 17, minus 1 is 16, we have to simplify. So the probability of king union diamond simplifies to what as a fraction? Which is approximately what? 0.31. Cool? So again, if you put in a fraction, it has to be simplified. Number 7 is tricky because there's a lot of possibilities. So, a number is chosen at random from the set of 2-digit numbers from 10 to 99. Okay? 2-digit numbers from 10 to 99. What is the probability that the number contains at least one digit 2? So we're starting at what number here? 10, and we're going all the way to what? 99. And we want to know the numbers that contain at least one digit 2. What's the first number that contains a digit of 2? 12. What's the next number? 20. Then what? 21. Then what? 22. Then what? 23. Then what? 24. Then what? 25. Then what? 26. Then what? 27. 28. 29. Does 30? Oh, 32. Then what? 42. Then what? 52. 62. 72. 82. 92. Those are all the numbers from 10 to 99 that contain at least one digit 2. Okay? Now, here's the problem. Okay? Here's the problem. The probability that a number contains at least one digit 2 is equal to the probability of 2 in the ones place. That should go there. Plus the probability of 2 in the tens place. Right? Now, if I look at all these numbers that I listed, the probability of 2 in the ones place is 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, right? The probability of 2 in the tens place is 12, 22, 23. I got those mixed up, but you know what I mean. 42, 52, 62, 72, 82, 92, right? So that was actually in the ones place. This is in the tens place. What do you notice? What do you notice? They overlap. So, to find this, after we find the probability of 2's in the 1's places and the probability of 2's in the 10's places, we're going to have to subtract the probability of their intersection. So I'm going to say 1's intersect 10's. Okay? Now, the probability is what we want over the total. How many total numbers did we have to choose from? Ooh, 89 or 90? The total is 99 minus 10, right? Which is 89. But is it inclusive? Do we include both 10 and 99? So we have to add 1, which gives me 90 total numbers. Okay? I have a total of 90 total numbers. How many of those numbers had 2's in the 1 places? So I had 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 9 over 90. Plus 2's in the 10's places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over 90. Minus their intersection. How many numbers intersected? Just 1 over 90. So the probability is 9 plus 10, which is 19, minus 1, which is 18, over 90, which simplifies to 1 over 5, which is 0.2. All right, one more. And this one's going to be really helpful for you on your homework because what it's going to do is it's going to help you organize your thoughts. All right? So on number 8, it says, at school, there are 16 students who study French and 21 students who study Spanish. There are a total of 30 students. Is this situation of mutually exclusive events? No? How do you know? Because you added them together, and what'd you get? 37, and that is definitely bigger than what? 30. They said they only had 30 students. And if I had 16 students in French and 21 in Spanish, that's more than 30, right? So these are not mutually exclusive. There has to be some overlap. So it says, draw a Venn diagram to illustrate the situation, then find the values that belong to each circle and the intersection. So let's draw a square first, or a rectangle, and inside you're going to put 2 circles that overlap. Okay? Circle on the left is French, circle on the right is Spanish. Now, when you have a problem like this, the easiest number to start with is their intersection. Okay? Their intersection is found by the difference between how many students are in the classes and the total number of students. So what did we say 16 plus 21 is? So 16 plus 21 is 37. But they said how many total students did they have? 30. So what is 37 minus 30? So that means 7 is our intersection. We only have an intersection of 7 students. 7 students are in both classes. Okay? Now to figure out the rest of it, you have to focus on the individual classes. How many students are taking French? 16. And we already allocated 7 of them to both. So what is 16 minus 7? 9. There are only 9 students taking only French. Okay? And then 21 students are in Spanish class, but 7 of them are in both. So what is 21 minus 7? So there are 14 students who are only taking Spanish. Okay, so part C says find the following probabilities. What is the probability that you are going to pick a student and they are going to be in French? How many students are in French? 16. And how many total students did we have? 30. And guys, I believe that you know how to make this into a decimal, so let's just simplify it. What would that be? 8 over 15. I'm good with that. You don't have to do any more. Okay? What's the probability that you are going to pick a student and they're going to be in Spanish? 21 over 30, which is 7 over 10. What's the probability that you pick a student and they're going to be in French class only? 9 out of 30. Good. And what does that simplify to? 3 out of 10. What's the probability that you pick a student and it's going to be Spanish only? 14 out of 30. And that's going to simplify to 7 out of 15. What's the probability that you pick a student and they're going to be in French and Spanish? 7 out of 30. Can I simplify that one? Nope. And then finally, what's the probability that I pick a student and they're going to be in French or Spanish? $30 out of 30? There's a lot of disagreeing statements. What do you think we should do? Probability of A plus the probability of B minus their intersection, right? So the probability of French, we already said was what? 8 out of 15, but I'm going to use this guy so we all have a common denominator. So 16 out of 30 plus Spanish, which was 21 out of 30, minus their intersection, which was 7 out of 30, which gives me 30 out of 30, which is, oh, look at that. So the probability that you pick a student and they're going to be in French or Spanish is going to be certain. It will happen because they're either in one or the other.